All right, folks, Professor Sackett-Taylor here. Let's wrap up chapters 11 and 12 with the conversation we're going to have now about the evolution of growth theory. So just a reminder, in the first part of this video lecture series, we talked about how we measure economic growth and why that's important. We gave a context to kind of the wealth of nations globally. In the second video in this series, we talked about the drivers of economic growth, namely being resources, natural, human, and physical, as well as institutions and the role that they play. And here we're going to look at how economists have developed the theory of economic growth and how it has changed over time. So we're going all the way back to 1776. You may or may not be familiar with the name Adam Smith. He wrote The Wealth of Nations, but he also wrote an inquiry into the nature and causes. And so this was like really the first real economics textbook, and its main focus was on what made some nations wealthy. So this was, the first time it was really a philosophical argument, not so much a mathematical argument. And it wasn't until the 1950s that we began developing as a discipline, a mathematical model of growth. And this started with the Solow model. It really still serves as the foundation for what we consider growth theory today, even though there have been changes and made to it to modernize it. So this growth theory begins with the production function. The production function is a mathematical function that describes the relationship between the inputs that a firm uses and then the outputs that it creates with those inputs. So here, small q is denoting output and small f is the mathematical function. So output is a function of, usually we give two arguments here, even though we know that resources come in a number of different categories, including land, labor, and capital. But here we're going to give it two inputs, which is physical capital, which we'll use K to denote, and human capital, which we'll use HK, and L to denote natural resources, land. So we've got an output, which is going to be the measure of GDP, the value of the output itself, which is a function of physical capital, human capital, and natural resources. So the very earliest version of the Solow model really focused on physical capital rather than natural capital or natural resources and labor. And the reasoning was because they were really looking at how, increasing the tools available would increase the output per worker. So essentially holding labor and natural resources constant, we were looking at those man-made tools, right? The things that we use in the production process itself. So what we saw was that capital in really wealthy nations exceeded capital in more developing nations, and that periods of investment growth in where they were investing heavily in capital led to periods of economic expansion. So we can see here, that there is a pretty strong correlation between the growth rate of investment in physical capital and the growth rate of real GDP, right? There's a positive correlation here. So investment is highly correlated with GDP growth, but correlation does not imply causation, right? So we need to be really careful not to be misled here, but there's something to look into. So if we focus on physical capital, we're really measuring the impact of the use of those resources. Economists think about this as what we call marginal product. Marginal product of a specific input is how much additional, that's what that word marginal means, the extra output associated with an additional unit of input. So here, there's really a couple of assumptions we're making in the model. We're assuming, first of all, that ceteris paribus, everything else is held constant, and the only thing changing is the level of input. And we're going to assume that we only add one unit of input at a time while holding all the other inputs constant. This is why the marginal product of input is always positive. However, what we're going to find is that as we add more of the input, more and more, that the marginal product is going to get smaller and smaller and smaller. So output is increasing at a decreasing rate. So if you're mathematically inclined here, you might notice that the marginal product is therefore measuring a partial derivative of the output function, the production function itself, with respect to a particular input. But if calculus is not in your wheelhouse, then forget the last words I just said. So here's an example of the production function, right? So on the x-axis, we're measuring physical capital, let's say like the number of ladders that you use in order to harvest fruit. And on the y-axis is your output, how many bushels of fruit you actually harvest per week. So input on the x-axis, output on the y-axis. And so the relationship here we could show in a table form. Like if we have 0 ladders, we can't reach very high, we can only harvest 1 bushel per week. If we add a ladder, we can now reach a little bit higher and we can harvest 4 bushels per week. So that's an increase of 3 bushels. So that's our marginal product from the first ladder. Essentially, that first ladder enabled us to produce 3 additional bushels. When we add a second ladder, because we're now dividing those ladders between the existing workforce, remember we're only increasing 1 input at a time, so we're holding everything else constant. So with 2 ladders, we harvest 6 total bushels. So that's an increase from 4 to 6, or in other words, a marginal product of the second ladder is 2 additional bushels. So the marginal product is like how much extra output we get from adding 1 more input at a time. So like 1 ladder to 2 ladders to 3 ladders to 4 ladders. And as we do this, we should see that like overall, the number of bushels that we're harvesting goes up and up and up, right? More input means more output. But the extra amount, that marginal product measure, is actually decreasing. That the additional amount of stuff we get from that input is going to get smaller and smaller and smaller as we add inputs. And this is because of resource crowding, right? Remember, we're holding everything else constant. So those ladders start to get, split among lots of different people, and we have some inefficiencies there. And not everyone is going to be, it's not like a 1-to-1 where like everyone gets a new ladder, right? So ladders will help us harvest more fruit, but it's not a 1-to-1 for each person. And so each ladder increases overall productivity, but the productivity increases at a decreasing rate. And what this looks like, if we were to graph it, is it looks like a log normal function. Again, if you're mathematically inclined. If not, forget what I just said. Just know that it's a curve that increases, but it increases fast at first, and then it continues to increase, but more and more slowly. It tends to like level out even. So the marginal product per ladder is declining as ladders are added. As we move horizontally to the right, we're adding more and more inputs, and the output is increasing at a diminishing rate. This is what we call diminishing marginal product. It's the output of each additional input getting smaller and smaller. All right, so all of that to say, this is the basis for the Solow model of growth. And there are 2 implications. If everything about this model is true, it means that the 2 implications, which I'm going to cover on the next slides, are a steady state implication and a convergence implication. So steady state, what this means is that what this model is implying is that there's a condition inherent in the macro economy of no new net investment, right? So what this means is that like there's a long run equilibrium point in which eventually, because of diminishing marginal product, we wouldn't continue to invest in capital, right? Like at some point you have enough ladders and an additional ladder doesn't help you. So you wouldn't buy that extra ladder. So there's some point at which there's no new investment, there's no change in the capital stock, and therefore the model would suggest no change in real income either. However, in reality, right, capital is really costly. And so capital will only be replaced when the benefits from, you know, an additional unit actually exceed the cost of investing in that unit. And so as long as the costs of capital are positive, this is going to happen at, you know, some point in the future in which we could think of this steady state kind of as like a stagnant state. Like it doesn't last forever, because when an economy reaches steady state, real GDP stops growing and therefore economic growth would stop. But once we reach steady state and we realize that like it's not worth the investment in the new ladder, something has to give, right? There's a point in which the cost of investment outweighs the gains in investment. So there's no longer an incentive there. So, you know, if we think about net investment as the cost of the, like the benefit we get from the investment minus its depreciation value, which is, you know, the fact that it depreciates or like wears away over time, that, you know, investment always has to be sufficient enough to offset that depreciation. So, you know, when net investment is zero, there's, you know, net investment is zero because there's like some things that are depreciating and we're replacing them, but, you know, there's still some positive investment there. So the capital stock might stay constant through replacement. So like this is going to naturally occur over time. Things tend to depreciate over time. You know, roads break down, computer programs become outdated. We have to replace them. So there's always some positive investment, even if it's just a replacement cost. The second implication of the Solow model is convergence. This is the idea that per capita GDP across nations would eventually equalize as each nation approaches its steady state, right? So like one nation experiences diminishing marginal product, we no longer find need to continually invest because the costs of investment outweigh the benefits that we receive from that investment. So we get to a point where we're just replacing what has depreciated. And as we kind of slow to a stagnation, other countries catch up, and eventually all the countries, you know, globally would equalize in their per capita GDP. Right? This would suggest that these poor countries should really catch up quickly, and that even at lower levels of capital, since they yield higher marginal product, this would continue to attract investment in those poorer nations, right? Like what this would mean was that we would continue to see new factories being built in these low-income countries. But, you know, this is like theoretical because, you know, theoretically, GDP per capita in these developing poor nations should grow at a faster rate than the developed nations. And if one nation reaches a steady state, you know, other nations eventually catch up, right? In other words, like countries with lower levels of GDP per capita should have higher growth rates. But we don't see that in reality. Developed nations in the past, you know, that have made big new discoveries, you know, have documented, you know, ways that they've made mistakes in the development process. You know, there's definitely something here that goes beyond the theory that this model is able to capture. Right. So here's a historical example. Let's consider a historical example here. So if this graph is the production function, right? It's increasing at a decreasing rate. We're measuring physical capital inputs on the x-axis and the value in terms of real GDP of the outputs, the production of goods and services using that capital on the y-axis. So we've got that as inputs increase, outputs also increase, right? Put more in, you get more out, but you get less out every time. So while overall total output is going up, marginal product is actually going down. So like, let's consider in 1980, right, the United States had a lot more physical capital, factories, tools, machines than China did. And this is one reason why real GDP in the United States was much higher than China. But in the years since then, China has increased its capital stock substantially and has grown much more rapidly than the United States. And so the solo model implies that the United States is closer to a steady state and therefore grows more slowly than China. And if the two nations were identical except for their capital, then China's growth rate should converge to the US output level. Obviously, there's a lot of assumptions behind this model of similarities that don't hold, right? So even though we saw this upward trajectory, and that we expect China just to catch up to the United States, China has actually exceeded the United States in terms of economic growth rates. So data does not really support this original version of the model. Growth in wealthy nations have far outpaced the growth of poor nations. Some poor countries have grown, but most poor countries have not. They've stagnated. There's no sign of convergence, meaning that we don't see an equalizing factor across per capita GDP globally. There's still a huge, huge gap between the rich and the poor countries, and that gap is widening. The wealthier countries are getting wealthier and wealthier faster, and the poorer countries are being left behind. So evidence doesn't really support the original solo model, and therefore economists have had to reassess it, right? So, we, in the second half of the 20th century, while we've seen in real life, most developing countries continue to stagnate instead of experiencing high growth rates, we see wealthy countries still experiencing strong growth rates, meaning they haven't reached a steady state while others are not converging. So we've actually seen more evidence of divergence, right? A widening gap between wealthy and poor. So there's something missing in this basic solo model. That's clear today. It was clear in the 1950s, but the solo model implies faster growth in developing nations, which doesn't match our reality. So when we look around the globe, it's clear that growth in developed nations has not stopped, and economists needed to reevaluate. So in the original model, we saw a strong correlation between capital and economic growth, right? The idea was workers are more productive when they have more and better tools. But capital alone is not enough to explain sustained growth. So this more advanced version of solo is going to take into account technology, right? Remember what I said in the earlier video lecture, part 2, was that it's not capital alone, it's not technology alone, it's how technology and resources work together that really promote growth, right? So technology is referring to like the knowledge, the process, like the how of what we do. And so there's a newer version of Solo 2, where we take into account technology and how like a zero growth long run equilibrium is actually completely avoidable if you continue to enhance your technological developments. So what this does is graphically, it essentially increases your marginal product of capital, shifting the production function upward. So in our new equation, we have our original production function where output was a function of physical capital, human capital, and natural resources. And now we're going to take into account this multiplier effect of technology. New technology is going to allow us to produce a higher level of output at any level of capital, right? So your inputs don't have to change if your technology is changing. So if the capital is embedding this new technology, the capital itself becomes more productive without needing to change the quantity of it available. So like, for example, today, personal computers are much more productive than they were 10 years ago. So the new solo model production function scales through this numerical constant, allowing for technological advancement. So the multiplier here, which is like capital A, is going to shift that graph upward, but not in a parallel way, because that's not how math works. So let me show it to you here in a graph. So here's the original, so here's like an original production function where A is small. And as A grows, it has this multiplier effect on each of the inputs. So the multiplier effect is larger at larger quantities of inputs, right? When you multiply two numbers together and you multiply the same number by a larger number, the output is larger. So the multiplier effect is pretty small here at K, but as I move to the right, the multiplier effect gets larger and larger, creating a larger gap between these two curves as I move horizontally to the right. The Solo 2 model also assumes that these changes in technology are exogenous, meaning they happen outside of the functional form itself, right? It's not inside of the function, it's outside of the function. So output is still a function of those three inputs, and there's an outside exogenous multiplier. This assumption is basically saying that like innovation occurs, but not because of the inherent characteristics of the capital inputs itself. So exogenous growth are like independent factors, essentially due to luck, right? Of like where these technological advancements occur. It's not like, oil is more productive in the United States than it is in Afghanistan. Oil is oil, right? Like the technology is not inherent in the input itself. Technology is exogenous or outside of the inputs of the model. So, technological progress is sometimes lucky or random, but like also keeping it exogenous helps us make the model mathematically beautiful and easier to solve. It really emphasizes the importance of the relationship between capital and technology. And so what this now implies, this new version of Solo, is that for these developing countries, these poorer, low-income countries to grow, it's not enough to continue to invest in capital. They also have to invest in technology at the same time. So the way that we could promote growth in developing countries, therefore, is in the wealthier nations, we could help by funding capital investment so that they can use their investment funding in technology. There's even a newer version of growth theory than Solo 2. We started to believe, as economists are looking at the real world data, that growth was spurred on by, reasons that were like particular to specific economies, right? Like some nations have something special about them that really promoted technological advancement while others did not. So the new growth theory approach really focuses on what drives technological change, not what drives investment in capital. And the thing that drives technological change are innovation incentives, right? What incentives or institutions are creating an environment ripe for innovation? So now we're thinking that that kind of technological advance is actually inherent in the model, right? It's endogenous. It's a factor inside of an existing economy because it's describing a relationship of like the rules, the laws, the policies of how an economy works. So now we add, we have this exogenous technological factor A that has a multiplier effect, but we also consider institutions inside of the economy, right? How do institutions set up an environment that, protects private property and provides incentives for innovation and, has a stable political environment and rule of law and promotes competitive markets, right? Like those are all institutional things that happen from inside of an economy. And so they become part of the growth function. So nations then have to be responsible for creating the environment that encourages technological change. They can create different incentives for individuals to change their behavior that either promote or hinder growth. So like broadly defined, there's going to be, good institutions and bad institutions. And the right institutions lead to economic growth while the bad ones don't. Positive institutions have a couple things in common. They're transparent and consistent. They protect private property. They have stable price systems. Whereas negative institutions that like hinder economic growth tend to exhibit high levels of corruption and political instability. So, we made this list in the last lecture, but I'm just going to really reiterate it here because this is now part of the growth model itself. We want political stability driven by rule of law. We want to protect private property rights, monitoring and enforcing them. We want to allow for competitive markets and limit the amount of market power that any one firm has to set prices. We want to see a free flow of products, goods and services, and monetary funds going across borders in trade. We need efficient taxes that raise revenue, but do not inhibit transactions, the production and consumption of goods and services by too much. And we need to keep our monetary currency and our prices stable through solid monetary policy. So, right, this is like where institutions themselves begin to determine incentives, and they decide how to spend resources in order to help people see that the expected payoff from their work is actually greater than the cost associated with it. Of course, there's a time lag, right, between what we do now and the benefits that we reap in the future. Like oftentimes payoffs from investing in something today are actually come a long time in the future. And we are often not patient enough for that kind of investment. We are very, very now centered. Our time preferences are really focused in the now. And this is a human trait. And one of the reasons why, we actually make really big mistakes when it comes to setting ourselves up for future growth by choosing potentially to make the investment rather than consumption today. All right, there is a lot of information in this chapter. So let's just summarize. We saw that the argument that economic growth is important can be made by simply looking at the context of the different wealth levels of our global economy and the different nations that contribute to it. It really has a historical perspective because we've really only recently seen huge, jumps in living standard. Economic growth is really central to the study of modern day macroeconomics. It helps us understand how we make living standards better over time around the world. It's driven by three primary things: resources, technology, and institutions. The solo growth model really emphasized capital and technology as the foundations of economic growth theory, but that implied a steady state, meaning we eventually stopped investing in capital and we saw a convergence of real per capita GDP across nations. That model just wasn't sufficient to explain what was happening. So the newer model, the Solo 2 model, really emphasizes the role of technology as an exogenous multiplying factor. But an even more modern theory highlights the role of institutions that foster endogenous growth. That is, you have to create the environment within an economy that are incentives for people to invest now to produce more later. Whew, that's a lot, but this is a really important chapter. It's going to set us up for where we're going next. We're going to look at fiscal policy and monetary policy, the ways in which the government as an institution creates the rules, the laws, the policies, the way in which our economy functions. And so we need to know what kind of the end goal is to figure out how to develop good policies around it. So a lot of cool things to look forward to, but for now, you can rest and I'll see you next time.